So in today's class sessions, we're going to be mainly going over two topics: IP addressing and then IP routing. We'll spend the morning talking about some of the just general overview of how IP addressing works, how IP subnetting works, the general logic of how a host sends IP traffic into the network. And then later this afternoon, we'll get into some more of the details of the different routing protocols like RIP, EDGE-RP, and OSPF that are going to be used for the routers to talk to each other and then exchange information about what the network topology looks like. So as we talked about before, the network layer of the OSI model, which is layer 3, this is where IP version 4 and IP version 6 are going to work. So the main role of layer 3 is going to be for logical addressing, which is like our IP addresses or our IPv6 addresses, where we saw with layer 2, which is the data link layer, that's used for the hardware addresses, like the MAC addresses in Ethernet, and some of the other layer 2 addresses we'll talk about like when we get to frame relay and serial interfaces. But the key here is that these logical addresses, we can assign them however we want. That with the physical hardware addresses, like the Ethernet MAC address, that's going to be assigned by the actual manufacturer when they create the card. And we don't really care about the details of the layer 2 MAC addresses because we'll see when we actually go to send IP traffic, the host stack of TCP/IP already has mechanisms built in to deal with layer 2 addresses. So from our point of view, if there's a problem with layer 2, we might be looking at like the MAC address table of the switches that we saw yesterday. Maybe we want to track down where an individual host is located. But from a layer 3 point of view, this addressing is going to be however we assign it. Now, this is also where path selection is going to occur, which is basically IP routing for IP version 4 or IP version 6, where the routers or the layer 3 switches that are running the different routing protocols ultimately are going to decide how the traffic needs to be sent through the network. Where the path selection that we saw at layer 2, that's generally going to be controlled by the spanning tree protocol, and how the Ethernet switches learn the MAC addresses when the host sends their ARP packets, the address resolution protocol. The layer 2 switches are going to automatically learn the MAC addresses and then figure out how the traffic should be switched through the layer 2 LAN. But in the case of IP routing, this is not going to be automatic. There's a bunch of different protocols that we would need to manually configure and design in order for the network to figure out what are all the IP addresses in the network, and then how do we ultimately send the packets, the data packets, which is what we call our layer 3 protocol data unit, or our PDU. So when we're talking about an IP packet or an IPv6 packet, we're talking about layer 3 of the OSI layer, or the OSI model. Now, the addresses themselves are 32-bit values, but the problem is if you look at a 32-bit string in binary, it's really difficult to decode, to figure out exactly what that means. So from our point of view, we're going to be grouping these together in 4 1-byte decimal numbers, which is known as the dotted decimal format. So when we look at like Windows and say ipconfig, we'll see that the addresses are going to be something like 1.2.3.4, which is easier to read than 32 binary numbers, either zeros or ones, over and over and over. But from the perspective of the routers and from the layer 3 switches, they're always going to be reading the numbers in binary. So the formatting of the decimal is just for our purposes, to make it a little bit easier to read. Now, each of these numbers that are separated by the dots, each of these are going to represent 1 byte, which means that in decimal, the range is going to be from 0 to 255. And one of the things that we need to look at today is how does the binary math work, or the binary logic of how the addressing figures out what network I am on, what network are other people on, and then ultimately how am I going to send the traffic to them. Now, in the case of the CCNA exam, this is one of the big sticking points that you need to spend a bunch of time practicing, is how do you figure out what network an individual device is on, or what subnet it's on, or if we wanted to figure out how many hosts do we want per subnet, or how many subnets do we have per network. So we're going to spend a bunch of time going through the different calculations of this today. But the key is that since these numbers are always represented in binary from the router's point of view, we're always going to be looking at 2 to some power, which in this case is 2 to the 8th for 8 bits per byte. And it means that each of the bytes is going to have a decimal range of 256 possible values. So it starts at 0. The maximum value is going to be up to 255. And each of these is what we call an octet, because there's 8 bits per byte. So each of these numbers that are separated between the dots, these are going to be our octets, where typically the addresses are referred to by their first, second, third octet, and fourth octet. Now, originally when the addressing was designed, they came up with what's known as the address class, which is subdividing the addresses into 5 different distinctions, which are classes A, B, C, D, and E. Now, classes D and E, these are going to be reserved for other special purposes. The class D is going to be for multicast addressing, which basically means that you can have one source sending to multiple destinations at the same time, like maybe a video server that's sending out a video stream and then you have multiple people watching it at the same time. So the classes A, B, and C, this is where we're mainly going to focus on. These would be what are considered unicast addresses, where the address is going to be assigned to one individual host, and then if host A is trying to talk to host B, they're going to be sending packets on a one-to-one basis or on a unicast basis. So when we're talking about IP routing, what we're actually talking about is IP unicast routing. There's other types of routing like IP multicast routing that would be for the class D addresses. But the class itself is going to be based on the 4 most significant bits of the address, which means that when we're reading the address from left to right, it's going to be the first 4 values in binary that's going to determine what the class is. And the first of which is the class A, is going to be any number that starts with binary 0, which in the case of decimal, this is going to be anything that's in the range of 0 to 127. So when we look at the addresses in binary, the binary ranges are going to go from 128, 64, 32, 16, 8, 4, 2, and 1. So for each byte, or each of the values when we're looking at the dotted decimal format, each of these values are going to represent 8 possible binary bit places, where there's some combinations here of zeros and ones that are eventually going to make up what the decimal number is that we're looking at. So when you're reading this number from left to right, anything that starts with a 0 in the first place, this is going to be class A. This means that when we're looking at this in decimal, that any of the bit places can be set except this one. So this always has to be a 0, which means the range would start at all zeros for binary, and the range would end when every other bit place is set to a 1. Now, the shortcut way to think about this is that if we were to set this bit, so if the address looks like this, a 1 and then all zeros, it means that in decimal, this value is going to be what? This value is going to be 128. So if every bit is set besides the 128 bit, like this, it means it's going to be 128 minus 1. So the range for class A is then going to go from 0 to 127. Where the class B addresses, they're going to start with binary 10. So it means that they're going to have a decimal range somewhere from 128 to 191. So likewise, if we were to look at that in binary, we have the 128, 64, 32, 16, 8, 4, 2, and 1. And if the bits are set where this is always a 1, this is always a 0, which is again for class B, it means that the starting range is going to be here, and the ending range is going to be 1, 0, 1, 1, 1, 1, 1, 1. Or in other words, it's going to be 128 plus 64 minus 1. Because if this bit here was set, then it's going to be a 64. But in this case, it's going to be 1 minus that. So it's every other bit set except the 64 bit. So essentially, it means that if we have 0 to 128 plus 64 minus 1. This is what the range is, or excuse me, not from 0. It's going to start at 128. So it starts at 128, and it goes to 128 plus 64 minus 1. Then the ending range is going to be 191. Now you'll see that there's a lot of different shortcut methods that people have come up with over the years that are related to addressing. Mainly I'm going to be focusing on the long way to do it in binary, because if you learn that way first, then you can learn the shortcuts afterwards, and you understand exactly what the shortcuts are going to actually relate to in the binary numbers. So that's our class B. Class B is going to be from 128 to 191. Then the next one, the class C, is going to start with binary 110, which then means that we have decimal 192 up through 223. Because if we have, again, 128, 64, 32, 16, 8, 4, 2, and 1, the bits are going to be set to 110. So these are always 110, which means that the rest of them can be any combination. It can start with 0, 0, 0, 0, 0. It can go all the way up from 1, 1, 1, 1, 1. So the starting range then would be 128 plus the 64 bit, which is 192. Then it's going to go through 128 plus 64, and then 1 bit less than 32. So plus 32 minus 1, which means it goes up to 223. So this is our class C range. The next one, the class D, is going to add 1 more bit. So class D starts with binary 1110, which again, this is going to be reserved for our multicast addressing. And this is going to be in the decimal range of 224 to 239. So if we did the same process as before, where the first bits are set to 1110, so 1110, then anything after that can be set. So all the way up to 1110, 1111. This is going to be 128 plus 64 plus 32, which is the starting range. So this is 224. Then it's going to go through the same values, 128 plus 64 plus 32, and then 1 less than 16. So plus 16 minus 1. So this is going to take us up through 239. Again, for class D. Then the last one, class E, is a reserved range that's not actually assigned to anything. And that starts with anything that is 1111. So it's going to be the final range that goes from 240 to 255. But again, remember, this is the first octet. So whenever you look at an address, just based on the first decimal number, you should be able to tell what class it is. Now, originally what these classes meant was going to control how we subdivide the address into 2 portions, which is known as the network address and the host address. So the overall idea of this is a hierarchy of addressing, kind of like your mailing address works, where the network address would be like your street, that I live on Main Street, and that the host address is like your house number, where you live at 100 Main Street. Now, the overall goal is that when we look at the IP routers in the middle of the network, when they decide how we're going to send traffic, they're going to be doing their routing procedure based on just the network address. So they get the traffic up to the device that's actually connected to that network. So like the default gateway of your host, then your default gateway is going to figure out what's the actual host address on that segment that you're trying to send the traffic to. So the network itself is really only concerned with the first portion, which is the network address. Now, originally the idea behind this is that the class A, B, C, and D were going to be subdivided so that a class A network would always have the first octet, or the first 8 bits, assigned to the network. this means that there's 24 bits left over for the host address. So when you look at this in dotted decimal format, it would mean that the first number is always the network number, and then anything after that could be any of the host addresses. So if we were to think of this in binary, it means that we would have, for class A, we would have 1 byte for the network, or in other words, 8 bits. And then the rest of it is going to be left over for the host. So the host address is going to have 3 bytes, which is 24 bits. So if we had a class A address that had a subnet mask that was 255.0.0.0, which is also sometimes denoted as a /8, it means that in the host portion you have 2 to the 24 as your possible number of hosts. So with a class A address, you would have 2 to the 24. So it's like 16 million hosts you could have in a class A network. Now, it doesn't really make sense that you would have 16 million hosts on the same network. So we'll take this number and then we're going to subdivide it into the subnetworks or the subnets, which are going to break it down so that there's less number of hosts per segment. But originally, this is what the specification said, that the hosts, that the class A addresses, that they're going to have 8 network bits, 24 host bits, which means you could have somewhere around 16 million hosts possible. With the class Bs, the second octet is also going to be for the network portion. So we'll have 16 bits equally for the network, 16 bits equally for the host. So the first 2 numbers, those are going to denote the network address. First 2 numbers are going to denote the host address, which means that if we were to take 2 to the 16th, so 16 bits for the host addresses, it means you're going to have somewhere around 65,000 possible hosts. Now again, we'll take this and we'll subdivide it, or we'll subnet it. So it means that out of these 65,000 possible combinations, we're going to break it down into much smaller networks. Then we have the class C addresses, which are going to have an additional byte for the network. So the first 3 bytes, or the first 3 octets, those are going to be for the network address. The last byte, or the last 8 bits, those are going to be for the hosts. So it means that, in this case, 2 to the 8th would be the amount of hosts, or basically 256 possible hosts, where we're going from 0 through 255 inclusive. Now, the original idea about this was that for Class A networks, that these would be assigned to large networks, like universities or service providers, that potentially they're going to need tons and tons of hosts. So they would get assigned to Class A, and then they can break this down to any smaller values that they want. Then the Class B is going to be for any type of mid-sized network, and Class C is going to be for our smaller networks that we only needed just a few number of hosts. But the problem then is that if we have a Class A network, it's not feasible to have 16 million host addresses. So we need some way that we can split this down into a smaller number of hosts per segment, or a number of hosts per network. And this is the whole idea of IP subnetting, where basically once we get assigned the addresses, or what we sometimes call our block of addresses, the network administrators can then further subdivide this for their own internal assignments. And when we do this, that's what the process of subnetting is called. So just breaking down the network portion of the address, we're going to create more networks, which means that we're going to have less number of hosts per subnetwork or per subnet. Sometimes this process is called borrowing bits, where we're basically taking the network division, where for a Class A, for example, we have 8 bits that are for the network. So this is the first octet. And then everything else after this is for the host addresses. So 6, 7, on and on and on. So the idea with subnetting is that this /8, which has the mask of 255.0.0.0, if we want to split this up into smaller networks, what we're going to do is take some of the bits that were previously assigned to the hosts and make these now as part of the network value. So if we were to borrow 1 bit from the host field and add this to the network, it means that we now have 9 bits for the network value, and that we have 23 bits for the hosts. Now, the way that you need to think about this is, what was the original assignment that the block of addressing was? So if we're assigned the network, let's say 10.0.0.0, which is a class A address. So it falls in that range of 0 through 127. The default classful mask or subnet mask for this would be /8, which is 255.0.0.0. If I borrow 1 bit from the network portion to make more subnets, it means that I'm going to have now 2 more networks, because it's 2 to the 1, how many bits I'm borrowing, so 2 to the 1 is 2. It means that now the network portion is going to look like this, where previously it was, when we look at the 128, 64, 32, 16, 8, 4, 2, and 1, and we do this on an individual octet basis or an individual byte basis. So 32, on and on and on. Where previously the network had these first 8 bits for the network. Now we're borrowing 1 more. This means that this value can be either now a 0 or a 1, but it's still used to denote the network. So if the first octet was a 10, and now the network can either be 10.0 with this first significant bit, or a 10.1, it means that the 2 networks we're breaking this up into are 10.0.0.0/9, because we borrowed 1 more bit, or 10.128.0.0/9. Because this bit here now, what was previously in the second octet as the host, it's now part of the network field. So we're breaking it up into 2 subnets. They're the .0 and the .128 subnet, which means that we have 23 bits left over for the hosts. If we take 2 to the 23, it means that now per network we have 8.3 million possible host values. So it's generally going to be about half of the value. For each time you continue to subdivide the network or to subnet it, you're taking your original value and you're breaking it in half over and over and over. And the end result of this is that we're going to have more hosts, we're going to have more networks, but less hosts per network. Now, the only restriction of this is that when we create more networks, there's 2 specific values that need to be reserved. It's the first address in the range and the last address in the range. And the first address in the range is needed for the network address itself. This is what the routers are going to use to figure out how do I actually route my packets in order to get there. The last address in the range is known as the subnet broadcast, or sometimes the directed broadcast. So again, the first one in the range is called the network address, or the subnet address. The last one in the range is the subnet broadcast, or sometimes called the directed broadcast. And the idea behind this is that we need an address so the routers know how to get to that subnet. Then there's also a value that we could send IP packets to everyone at the same time on that that subnet, which is our broadcast address. So when we compare this to the layer 2 addressing that we were talking about yesterday, for Ethernet MAC addresses, they use the value of all ones for the broadcast, which we have our 6 bytes for a MAC address, and this is in hex formatting. So this means that the all host broadcast at layer 2 is all Fs. This is what we would use, for example, for our address resolution protocol. Or we'll see later we could use this for like a DHCP request to try to get an automatic IP address assignment from a DHCP server. But this is used just at layer 2 for Ethernet MAC addresses. For IP at layer 3, we're doing the same logic where we have 4 bytes in decimal that we're denoting it as, which means that the IP broadcast address is 255.255.255.255. So if you were to send a packet to this address, it means that it's going to anyone who's running IP in your connected layer 2 network, like any host that's in your same VLAN. And this is one tool that you can use on the iOS to figure out who are the hosts that are currently in my IP network. So here on router 1, if I were to send a ping to the address 255.255.255.255, anyone that is running IP should respond to me when I send those packets out. So it means that I have So it means that in my VLAN, I have the host .7, 5, 3, 8, and 6. And by default, we can see the router is sending 5 pings. So one of them was needed for the ARP request. So this one, we didn't get a response in time because it took the routers a little bit of time to resolve the IP address to the MAC addresses. But once they did that, then everyone that was in the same IP network is going to send an ICMP echo reply. Now, this is actually kind of a security vulnerability, and we'll talk about this a little bit later when we get into some security topics. But most of the time, operating systems are not going to allow you to do this. Like if we try this from Windows itself, I don't believe that this is going to be valid to send pings to that address. So it's not going to allow you. Some OSs, it'll just say that the all host broadcast is not allowed. But essentially, when a device running IP hears a packet that has this address, it knows that it's destined for itself plus everyone else, so it's going to send any replies to this. So when we look at some of the network applications like DHCP or DNS, we can use this address to try to send packets to everybody at the same time. Now, inside an individual subnet, this is going to be part of then the subnet assignment. So if we had the network previously that was 10.0.0.0/8, which again has the subnet mask of 255.0.0.0, it means that the network address is going to be when the host has all zeros in the second, third, and fourth octet. So the network address of 10.0.0.0/8 is simply 10.0.0.0. The subnet broadcast is going to be when the host field is all ones. So this would be 10.255.255.255. So here it's kind of straightforward to read because the subnet mask is a nice round number. But as you start to create more subnets, this is where it can get a little bit confusing that you need to basically manually calculate what's supposed to be the network address for that particular host, and then what would be the last value, the subnet broadcast. So then if we were to split this into two networks, 10.0.0.0/9 and 10.128.0.0/9, it means that the network address of this first one is 10.0.0.0. The broadcast address would be all ones, with the exception of that one bit that we had to borrow for the network address. So here we borrowed one bit, which means in the first octet we're still going to have 10. But in the second octet, when we look at this bitwise, or in binary, it means that this value here is now for the network. So the subnet broadcast is going to be when all of these are set to a 1. So for the first network, when that is a 0, its subnet broadcast would be 10 dot, the first bit being 0, and then everything else being a 1. Or in other words, the subnet broadcast would be 10.127.255.255. So if I had this subnet directly connected on the router, and then I pinged this address, 10.127.255.255, everyone that's in that network is going to receive that packet. Then likewise for the other network that was set to 10.1, with 1 being the first bit place, the subnet broadcast would have all 1s, which means that it's 10.255.255.255. Okay, any questions up to this point so far? Now, originally when subnetting was used, there was a restriction that all subnets in the network had to have the same subnet mask, or basically it means that you have to divide the major network that you were assigned into an equal number of subnets. So it means that all of them had to have the same subnet mask. And this had to do with the limitation of some of the routing protocols, like the original RIP version 1 routing protocol, or Cisco's original proprietary IGRP protocol, the Interior Gateway Routing Protocol. And it was due to the fact that these were known as classful routing protocols, or essentially when they advertised to each other the information about the network, they didn't include the subnet mask along with their advertisement. So it means that if I were to take a /8 and break it into multiple /10s, for example, it would mean that every subnet had to have /10 everywhere. And then when I sent my routing updates, I'm going to automatically assume that every network is always /10, because everything has the same subnet mask. But once the routing protocols were fixed to do this, then this limitation is lifted. And essentially all protocols nowadays support this feature, which is known as classless routing. So when we look at RIP version 2 and EHRP and OSPF, these are all classless routing protocols, and we don't have to worry about all of the subnets having the same subnet mask. But the problem with this originally was that it made your design of how you were supposed to subnet, or how you're supposed to break the major network up, makes it a little bit more difficult, because you generally ran into one of two problems. The first was that if your subnet was too small, you couldn't fit all of your hosts in it. So if I want 130 hosts on an individual network, there's going to be a limit to how far I can create the subnets. But then you also had the problem on the flip side, that if the subnet was too big, you end up wasting a lot of address space. And this especially came in cases where you had point-to-point WAN links, where a point-to-point link basically means that there's just two devices on the network. Like here between router 1 and router 3, I don't need to say that on this network I want 8 million possible hosts. because in reality there's only two devices running IP. There's router 1 and router 3. So this means that if I were to create my subnets, even if everything was a /24, which means the mask 255.255.255.0, which gives you for the host portion a range of 0 to 255, or essentially 256 possible combinations. So even if I went as far as /24, I really only need two address assignments here. I need router 1 and I need router 3. So it means that there's going to be 252 other values that I don't need to, that I can't use. I don't need to assign them, but they're now allocated, and they can't be assigned to anybody else in the network. Now we'll also see a lot of times in today's network, the subnet design is not as important as it used to be, because it's very few and far between you'll see a network is using what's known as public addressing versus private addressing. And we'll talk about this when we get to the network address translation, or the NAT feature. That since most of the routers are pretty powerful to begin with nowadays, it's not really going to matter that you have to have the most optimal design of your IP subnets. So if I'm using a private address like the 10 network, it may not really matter that I'm wasting 253 addresses on this link. But originally this was a big concern because everyone was allocated public addressing, and then they assigned this to all of their end hosts. So to fix this, they came up with what's known as variably length subnet masks, or VLSM, where VLSM basically means that your subnet mask could be of any arbitrary number that you want to define. So if I were to have a network that is, let's say, 100.200.0.0/16, and this is what I was publicly assigned by what's known as the Internet Assigned Numbers Authority, or IANA. So they're the standards organization that actually assigns the addresses to everybody. So I asked them for an allocation. They said, for your network, use 100.2.0.0. And this is a class B, so you have a /16 on this, which is the classful mask. But now I want to break this down into further subnets, or to smaller values. So let's say that we wanted to take this and break it down into /24 subnets, where originally the mask was 255.255.0.0. I'm going to borrow an additional 8 bits from this field, so that the result is my subnet mask is 255.255.255.0. So I'm moving from /16 to /24. It means the difference between these, 24 minus 16, or in other words 8, this is the amount of bits now that I can use to create other networks or other subnets. So if we were to take 2 to the 8th, which is 256, it means that including 0, I have the possible ranges of networks that would go from 100.200.0.0/16, 100.200.1/16, all the way down the line, all the way up to 255. So now I have 256 extra networks that I made out of this one original subnet. And these are, these are not /16 anymore. These are /24s. You'll see that a lot of times on like an Ethernet LAN or like a wireless network, a lot of times /24 is used because it ends up to be kind of a nice round number. And you rarely run into the case where you need more than 250 hosts on an individual subnet. But you technically could go further than this. So let's say that I want to break this into, let's say /28. And this is where it starts to get a little bit more complicated, and you need to start to work this out longhand. So if we were to break this into slash 28 means the first two octets are going to stay the same. They're going to be 100.200. The third octet is now becoming part of the network. And out of the last octet, so up to here, I have 24 bits. I'm going to borrow an additional 4 for the network. So there's 4 network bits. There's now 4 host bits. Originally, this was a slash 16. I'm trying to break it down into multiple slash 28s. So the difference between these, 28 minus 16, this is now how many bits I have for the network portion. So if we take 28 minus 16 is 12. 2 to the 12th would then be the possible number of networks. So 2 to the 12th means that I have now 4,096 networks. On each of these networks, I have 4 bits that are left for the host addressing. So it means out of 4,096 networks, I have 2 to the 4 number of hosts. Or 2 to the 4th is 16. So 16 hosts per network with 4,096 possible networks, or 4,096 possible subnets. Now remember that on each of these subnets, we're always going to lose 2 of the addresses, though, because one has to be for the network itself, one of them has to be for the subnet broadcast, or the directed broadcast. So in reality, I only have 14 usable hosts. So in a lot of practice questions that go through subnetting, the question may be formatted that way that says, I want this number of hosts per network, and figure out what's the subnet mask that I could use in order to accomplish that. So let's say that for some of these networks, I need more than 14 hosts. Maybe I need something like 72 hosts, that I have some subnet that has 72 Windows machines or 72 devices, and I need to make sure that I can fit this inside of this network. So the longhand way to do this would be to look at what is this value in binary. So if we take 72 in binary, and the problem is in the exam you're not going to have access to the calculator, so you're going to have to do all of this longhand. But we'll look at some of the shortcuts afterwards, how we can do this. So here, if I were to take 72 from decimal to binary, it's 1001000. So 1001000. It means that when I mask the number of bits that go to the network, the last octet is going to have 8 possible bit values, where they are 128, 64, 32, 16, 8, 4, 2, and 1. So when we look at this value, which is 72 possible hosts, in binary here, this is 0001001. It means that when I create the number of bits that go to the network, the farthest I can go is here. So this could be my last network bit. The rest of these are going to have to be for the hosts, because otherwise I can't fit that many hosts in an individual subnet. So if we're talking about just the last octet here, it would mean that a subnet mask that is going to fit 72 hosts in it would be the first 3 octets. So the first octet is going to have 8 bits. The second octet, likewise, is going to have 8 bits. Third one is going to have 8. And then in the fourth, I can only borrow 1. The rest of them, the other 7 bits, those are reserved for the hosts. So it needs a subnet mask that's going to fit at least 72 hosts in it, would be 8 plus 8 plus 8 plus 1, or a /25. Now, when you look at the actual subnet mask that's going to be assigned to this, you essentially count from the left and add these numbers. So here, the only other bit that I'm setting in the fourth octet is the first one. So here, these 8 bits, when they're all 1s, they're all 255s. If I'm adding one more bit here, it means that this bit is going to be set. So this would be 128. So in the decimal notation, the /25, this is equal to 255.255.255.128. If this originally came from a network that was 100.200.0.0, it was originally /16, and I now broke it down into /25 subnets, assuming I'm doing this equally, so I'm breaking it all into /25 subnets, it would mean that I have 25 minus 16, or in other words, I'm borrowing 9 bits for the networks. Which means that the number of networks then would be 2 to the 9th, or 512. So out of this /16, if the mask is changed to /25, it means you have 512 possible subnets. And on each of those subnets, since there's 7 bits for the host, we have 2 to the 7th, or 128 host addresses, minus 2. Because remember, one is for the subnet, one is for the network. So you'll see there's tons and tons of practice questions that are out there with subnetting. A lot of times you can also find some automatic tools to do this. And in a real design, you're probably better off, like in your actual network design, you're better off using one of these calculators just so you don't make a mistake. But in the case of the CCNA exam, you're not going to have that, so you're going to have to do it longhand. So if you were to just search for subnet calculator, there's a lot of utilities that people have put together to do this. The first hit here says, put whatever your value is. So let's say what I had, 100.200, 100.200.0.0, and the subnet mask was a /25. 192. So this one's not that great then. Let's see, class 100, 200. It was checked as class C by default. So dot, well, there's other ones besides this that would do the same thing. But on Cisco's documentation, there's a good reference that you can use for this. Problem is it's not very easy to find. So if you go here to support, then at the bottom go to configure. And I'll run through this once quick and then go back through it again. Under products, this is under security, firewalls, firewall appliances for the ASA. So it's part of the firewall documentation. Under these configuration guides for ASA, it doesn't really matter what the software version is. Let me say like 8.4 is one of the newer ones. But all the way towards the bottom, there's this reference appendix that has addresses, protocols, and ports. And this could be a useful document that you may want to bookmark. It goes through some generic things about IP addressing, like an IP address is a 32-bit number written with 4 octets. It shows you what are the classes of addresses. Because Class A has 16.7 million host addresses, Class B has 65,000. You can use subnet masks to break these huge networks into smaller ones. Okay, also tells you what are the private networks. We'll talk about this again more when we get to network address translation. But these numbers, these are defined by RFC 1918, which is the private use addresses. Like when you have your router connected to like your cable modem or your DSL, you typically see it's going to give you like a 192.168 address or 172.16 to 31. So these ones are reserved by the IANA for those private use. But then here it has this table for the subnet masks. So based on that bit length, how many hosts would that be per network? And then what's the dotted decimal version of this? We'll also see that when you get to the router's command line, there's a couple shortcuts that you can use on the router itself to see if your subnet mask is right. And it has to do with how it does its lookup in the routing table, which we're going to talk about in more detail today. This one here, it says do not use. Technically, that's not valid anymore. You can use a /31, which means just 2 addresses. Originally, they said not to use this because normally when you create a subnet, you need to leave those 2 extra addresses for the subnet address and for the broadcast address, which in this case, if you use a /31, it doesn't give you that. It gives you just 2 values. But in newer code and newer operating systems, it's not a problem. So you would typically see this is used for like a point-to-point interface, where again, if you have just 2 devices, like router 1 and router 3, I know that I only need 2 addresses on there. Whatever the first address and the second address, we could put this as a /31. Previously, the furthest you could subnet was a /30, which gave you 4 addresses. But then, since we need 2 of them for the subnet address and for the broadcast address, it means that you had 2 left over. But current ones, you see that you can actually use /31. You may see in like some of the CCNA books, they say don't use /31. Probably if I got this question on the exam, I would say that /31 is not valid because that's originally the way that it was defined for CCNA. But technically, you can use this. Then here it goes into some more details like the subnet mask calculation. Okay, it also gives you a quick reference for IPv6. We'll be talking about this a little bit later, how the address format for that works. Then it also goes over what are some of the different IP protocol numbers. This we'll talk about later when we get into routing and how stuff works at layer 4 and above when we're dealing with like TCP or UDP, OSPF, EDGRP. These are the different layer 3 protocol numbers that are part of the IP version 4 header. So again, it's kind of difficult to find here, but if you go to from the main Cisco page, it's under support. Then all the way at the bottom, under configure. Then products, security, firewalls, firewall appliances, ASA 5500, the configuration guides, whatever the version is. You can pretty much choose any of these. And then at the bottom, it's under reference and addresses, protocols, and ports. You could probably just search for this. If you searched ASA addresses, protocols, and ports, it'll probably link you right there. But again, the issue is that with the CCNA exam, you're not going to have access to this type of stuff, and you're not going to have access to a calculator. So typically, what I would recommend to do is when you get into the exam, they will give you one of those dry erase boards to make notes on. Write out the binary places, and then also maybe the common subnet masks like 255, 255, 255, 0. Then the next one would be 128. 128 plus 64 is 192. Plus another 32 is 224. Plus another 16 is 240. Plus another 8 is 248. Plus 4, 252. Then plus 2 and 1, these would be dot 254, and then dot 255. So the subnet itself, the subnet mask is always going to end in one of these values, because it has to be a sequential number of bits when you're counting from the left to the right. Now, if you look at these values, let's say 224, for example. One of the shortcuts that you can use is that if you take 256, which is the total possible number, so 0 through 255 inclusive is 256 values. You take 256 minus the last number in the subnet mask is 32. This is the number of usable addresses in that subnet. Now, two of these, again, you can't use because one is for the network address itself, one is for the broadcast. So it means that really there's 30 usable addresses in that subnet. Okay, assuming it was 255, 255, 255.224. If it was a 192, if you take 256 minus 192, that likewise is going to be how many addresses we have there, which is what here? 64. This number as well, the amount of hosts, this is going to determine where the number of networks start. Okay, what the network addresses are. So if you were to take 256 minus 192, okay, so it's a range of 64 for the host addresses. The first subnet is going to be 0. The next subnet is 64. If you keep adding 64, these are going to be the network numbers. So the subnets would be 0, 64, 128, 192, and then that's it to get to 256. Okay, we'll see when we talk about routing next. This is how the router and the end host that's running IP, this is how they ultimately figure out, is the destination on the same network as I am, or are they on a different network, and do I need to route traffic in order to reach them? So again, with the variable length subnet masking, or the VLSM, it just means that you could take your network and you could split it into multiples of these. So it's any arbitrary numbers that you want to use, as long as when you're counting from left to right, which is your most significant bit to your least significant bit, it has to be sequential. So the subnet mask would always be like 111 0 0 0 0 0. You can't have a subnet mask that says like 111 1 0 1 0 0 0. It always has to be sequential with the bit values. But what this allows you to do is, if we took that same example where we have the 100.200, .0.0/16. I could break this up into /24s. And how many /24s would I be able to get out of this? It's going to be 24 minus 16 is 8. 2 to the 8th is then the number of networks. So it's 256 possible networks. So it's the 0 address through the 255. But what you could also do is say that maybe for half of these, I want them to be /24, and then I want other ones to be different mask lengths. So you could have 10 or 100.200.0.0/24 up through .127. And then maybe everything after that, I want to split those into smaller ones, to /26s or /28s. And this is essentially what VLSM says, that just because these ones are /24s doesn't mean that these ones have to be /28s. And when we look at routing, and if you were to look at this on the internet and look at what the internet's routing table looks like, you're not going to have all the same subnet mask. All sorts of different networks are going to have different lengths. And if we look at an example real quick of this, we're going to take a break in a second, but there's these routers on the internet that are called route servers, where the different service providers host them. Like this one is hosted by AT&T. And the usage of this is that if you're trying to change how traffic is routed from the internet back to you, you can look at what is my address that I'm routing to. Like if we look at here, let's say what is my IP? Let's see, what is our address here? Is this value, this 173 number. On this router, if I were to say show IP route, and then the address that we're using publicly, they're using a /13 subnet to reach us. But that doesn't necessarily mean that here we're actually using /13. So the idea behind IP addressing is that it has this hierarchy where you can take these subnets and then you can also combine them into the other direction, which is considered a supernet. So supernetting would be to create less network bits. Subnetting is to create more network bits. But if we look at the actual routing table of this device, if we show IP route, you'll see that the vast majority of these networks don't have the same subnet mask. Where some of these are /24s, some of them are /20, some of them are /22. And basically this is every single route that's in the internet. So there's about 300,000 of them in here. What's that? 17. This one /17. So this router here, it actually has 372,948 routes. So that's the whole internet. But if you look at the full address space, which is 32 bits, it would mean 2 to the 32, that's our possible numbers. So it's what? It's 4.2 billion. The problem is that you can't have 4 billion routes in the router. It's not going to be able to handle that. So when we look at the routing, one of the techniques that you can use is that in your own network you can subnet your addressing to however you want. But then when you use the routing protocols to advertise this, usually you don't advertise all of the individual subnets. We kind of collapse them backwards so they end up looking like the original values that they came from, like the /16 or the /17, etc.